Okay, welcome everyone to the second lecture of the day. We are very happy to have Shu-Heng Shao, who is going to give us today the first lecture of his course on anomalies of global symmetries. Please, Shu-Heng.
Okay, yeah, thank you for inviting me to give lectures at the school. In the invitation, I was asked to give lectures on anomalies of generalized global symmetries. But then I realized for school, maybe it's better to start with the ordinary global symmetry. So I hope it won't be too boring for some of the audience. But I think there are something interesting to be said, even just for ordinary anomalies. Okay, so this lecture will have three parts. I will start with the simplest possible setup, namely anomalies in quantum mechanics, or in 0+1D if you wish. And then I'm going to talk about anomalies in 1+1D, and in particular, I will focus on the free compact boson theory in 1+1D. And finally, I will talk about Z2 anomaly for bosonic theory in 1+1D. And somewhat contrary to the main goal of the Bootstrap program, most of the models that I will discuss in these lectures are free theories. And they are completely solvable, but yet they have very interesting anomalies. And starting from there will be non-perturbative results that we can derive. All right, this is the outline. So let me start with a very standard and brief introduction on what we mean by global symmetry. So global symmetry should be contrasted with another very popular notion, the gauge symmetry. Global symmetry is intrinsic, meaning that it acts non-trivially on operators and states in our theory. So our states should fall into non-trivial representations of the global symmetry. On the contrary, gauge symmetry is ambiguous. For example, there could be a gauge symmetry in one presentation of the model, but not in another presentation of the model. Because it's ambiguous, gauge symmetry leaves all operators and states invariant. One simple example of this comment is the 2+1D Maxwell theory, the free Maxwell theory. It's exactly dual to a free compact scalar. In the Maxwell presentation, there's a U1 gauge symmetry, but in the compact scalar presentation, there isn't such a U1 gauge symmetry. For global symmetry, it can have Tahoef anomalies, and that will be one of the main topics of these lectures. On the other hand, gauge symmetry cannot be anomalous. When the gauge symmetry is anomalous, then the theory is simply ill-defined, and we should not talk about it at all. So let me give a very quick general discussion about what a Tahoef anomaly is. And for this discussion, I highly recommend the introduction in this very recent paper. So given a quantum system, it could be a quantum field theory, for example, with a global symmetry G, we can couple the system T to the classical background gauge field A of the global symmetry G. And here I highlight the word classical and background, meaning that this gauge field is a fixed value in our partition function. And we do not integrate over classical background gauge field. So the partition function can be schematically written in this way. We integrate over the dynamical fields collectively denoted by phi. Our action consists of the dynamical fields coupled to these background fields. And at the end of the day, the partition function is a function or functional of the gauge field. On general grounds, we are allowed to modify our action or our coupling to the background fields by classical local counterturns of the gauge field. This amounts to different regularization scheme that we can choose in the ultraviolet. And we should always work with this freedom. The background gauge field here, which is denoted by a capital letter, should be contrasted with the dynamical gauge field which will be denoted by a lowercase letter, a dynamical gauge field will be integrated over in the path integral. Starting from a quantum system with a global symmetry G, and we couple it to some background gauge field capital A, sometimes, but not always, we might be able to promote such a classical gauge field to be dynamical. And this is the procedure known as gauging. When this is possible, what we do is simply to path integrate over the dynamical fields on top of the other dynamical fields phi, and we obtain a new quantum system, which I denote by T prime. Right. Here, I'm just trying to set up the stage to contrast the classical versus the dynamical gauge field. And this distinction will be important throughout the lecture. So what is a Tahoef anomaly? The obstruction to gauging certain global symmetry is known as the Tahoef anomaly of that global symmetry G in the quantum system T. More specifically, the Tahoef anomaly is signaled by the anomalous background gauge transformation. So we have this background gauge field A, and we can perform a gauge transformation on the background gauge field as well as on the other dynamical fields in the system. When we perform this gauge transformation, if the partition function is not invariant, but the non-invariance is only a phase, this phase is known as the Tahoef anomaly of the global symmetry G. Here, XD is the d-dimensional space-time manifold of the quantum system T. And this anomalous phase generally depends on the group element that we perform the gauge transformation by and the background gauge field. As I mentioned before, we are always allowed to modify the partition function by any d-dimensional local counterterms of the background gauge field. By adding such a local counterterm, we will modify this anomalous gauge transformation. Sometimes we might be able to completely remove this phase by adding such a d-dimensional local counterterms. But when this is not possible, this is known as the Tahoef anomaly. So Tahoef anomaly should really be thought of as all the consistent anomalous phase that cannot be canceled by choosing an appropriate d-dimensional local counterterms. And this is some kind of cohomology type question. And that's the reason why the classification of anomalies generally are given by some cohomology type mathematical object. One convenient way to classify or characterize an anomalies is through the anomaly inflow mechanism. So as I said before, even though the anomalous phase cannot be canceled by a d-dimensional local counterterm, it can generally be canceled by a d+1 dimensional local counterterm. So more specifically, let Y be the d+1 dimensional manifold such that its boundary is the spacetime manifold of our quantum system. There's a typo here, this should be plus. Then it's generally the case the anomalous phase, this guy, can be canceled by the gauge transformation of an invertible classical field theory in one dimension higher. So what do we mean by invertible classical field theory? The action is given by, schematically, this omega of the background gauge field A. It doesn't have any other, in this presentation, it doesn't have any other dynamical fields. It's just a classical function of our classical gauge field A. The partition function is then just the exponentiation of omega. You can think about it as this piece. So that explains the adjective classical. It's called invertible field theory because the partition function is always a phase. It's just e to the I, the integral of this omega. This is to be contrasted with a general quantum system where the partition function takes a more general path integral form. It's generally not a phase. For general anomaly, this anomalous phase can be canceled by the anomalous gauge transformation of this invertible classical field theory. If the D+1 dimensional manifold is closed without
Shu-Heng, is it also implied that this omega of A has to be a local function of A or not necessarily?
it's a local functional of A.
Okay, so it's a, and when you say it's a phase, do you impose a restriction that it has to be a real local function of A, or is this not important?
It's important, yeah. So it will be, for it to be a phase, this has to be real. Yes.
Okay.
All right. So yeah, so generally the anomalous phase can be canceled. Okay, let me rewind a little bit. If we take this omega of A on a closed manifold in D+1 dimension without any boundary, then it's going to be gauge invariant. However, if the manifold has a boundary, then it will pick up an anomalous gauge transformation. And the omega will be chosen such that it cancels exactly the anomalous gauge transformation here. In condensed matter literature, this invertible classical field theory is the low energy description of what is called a symmetry protected topological phase, or simply SPT. So I will use the term SPT and invertible field theory interchangeably in the following lecture. So everything so far is rather general and abstract, but later on I will try to give explicit example where this alpha can be written down explicitly. This omega also has a simple expression. But for now, let me just give a general introduction to the idea of Tahoef anomaly.
When you use the phrase generally, does this mean, what does that mean? Is there some mathematical abstraction to potentially writing it as a surface term in D+1 dimensions?
So I think that's a good question. So the anomalous, so if I just stay in D space-time dimensions, the anomalous phase has to satisfy various consistency conditions, and it's subject to some ambiguity, as I was saying here. So it's generally some cohomology element. One can ask, how do you classify all such anomalous gauge transformations? One can show that all these conditions can be satisfied by the invertible classical field theory in one dimension higher. But I don't know of a general, I don't know how rigorous that proof is, and I don't know how general that proof is. And it might boil down to a matter of semantics. Namely, if there could be some cases where the non-invariance of the partition function is more violent than just such a phase. And maybe in that case, it cannot be canceled by such an invertible field theory in one dimension higher. But in that case, I think it might boil down to what we really mean by global symmetry and what we really mean by an anomaly. So for the rest of these lectures, I will only focus on standard enough anomalies such that the anomalous phase can be simply canceled by an invertible field theory. And I will not make a general or completely rigorous statement about the most general possible cases.
Can I ask a question?
Yeah, go ahead.
So is it always true that we can have a higher dimensional manifold such that its boundary is the given manifold? So that we can, so this by D+1 is a higher dimensional manifold whose boundary is the given manifold. So is it always possible to choose such a manifold such that we can cancel the anomaly?
So generally, let me think about how to say that. So generally on this manifold, we not only have to further specify some additional structures. So for example, it could be a spin structures and other kinds of structures. And it's a non-trivial question to ask whether that can be extended to one dimension higher, preserving the same structure. I think for the cases I will discuss, this is always possible, but I will try not to answer the most general possible case.
Okay, then.
Any other question, or should I proceed? Okay, let me proceed. So in the presence of such a Tahoef anomaly, there's nothing wrong with the exact global symmetry G. There's also nothing wrong with the quantum system T. We just cannot gauge the global symmetry in that quantum system. So even though the English word anomaly might imply something bad, there's actually nothing bad about the global symmetry nor the quantum system. In fact, the Tahoef anomaly is very useful for constraining the dynamics of the quantum system. Furthermore, the Tahoef anomaly is an intrinsic property of the global symmetry, and it's generally rigid, namely that it cannot change continuously under RG flow. And that's the reason why it has to be matched between the ultraviolet and the infrared. And that's the reason why it's an important tool in analyzing strongly coupled quantum systems. So for example, the Tahoef anomaly might be labeled by some discrete number, maybe value in Zn. And since it's discrete, it cannot change discontinuously as we go to the low energy. And for many of you, we might have learned some other kinds of anomalies when we learn quantum field theories. And usually we learn anomalies starting from the 3+1 dimensional gauge theory. And there, if we have a U1 global symmetry, the anomaly comes from the famous triangle diagram. But there are many different notions of anomaly, so it might be useful to compare them at this point. So the famous, so in the triangle anomalies, at each vertex, we can put either a global symmetry current or a gauge symmetry background gauge field. Depending on what we put, they have distinct physical meanings. The worst possible anomaly is the gauge anomaly, where all three legs are gauge symmetries. For example, in the standard model, we should check the gauge anomaly of, say, put SU2, SU2, and SU2 here. The gauge anomalies have to vanish. And the presence of the gauge anomaly means that the theory is not healthy, and the gauge, and therefore there's no symmetry to talk about at all. Then there's a different kind of anomaly, usually known as the Abj anomaly, where one of the legs is the global symmetry, and the other two legs are the gauge symmetry. For example, you can consider the U1 QED coupled to a single Dirac fermion, and then you take the classical global symmetry to be the axial U1, and the gauge symmetry to be the U1 gauge field. Then as Abj realized decades ago, that classical global axial U1 symmetry fails to be a true quantum symmetry. So in that case, the U1 QED is, of course, well defined, but there isn't such an axial U1 symmetry at the end of the day. Finally, the main focus of the talk today is the Tahoef anomaly, where all three legs are global symmetries. And in that case, there's nothing wrong with the symmetry, and there's nothing wrong with the quantum system. The presence of a Tahoef anomaly in the UV forbids the IR to be trivially gapped. This is because there has to be something non-trivial in the low energy to match that non-trivial Tahoef anomaly in the UV. By trivially gap, I mean a low energy phase where we have a unique ground state and there's no long range entanglement, meaning that there's no non-trivial TQFT in the low energy. So with a Tahoef anomaly, the possible scenarios in the low energies are either it could be a symmetry preserving gapless phase described by a CFT matching the anomaly, or it could be a symmetry preserving gap phase described by some non-trivial TQFT matching that anomaly. Or the symmetry might simply be broken in the low energy. Some of these options might overlap with each other, and some of these options are not always possible. For example, option 2 is not always possible. And for example, it's not possible in 1+1D. In any case, the presence of an anomaly rules out certain scenario in the low energy.
Can you remind us why is it not possible 1 plus 1D?
So this is based on the classification of TQFTs in that space-time dimensions. So generally, if you are in high enough space-time dimensions, then we can have all kinds of topological operators, line operators, surface operators, and they might braid non-trivially with each other, so and so on. In 1 plus 1D, the dimension is too low. And basically, all the non-trivial dynamics are encoded by the local operators, the topological local operators in the 1 plus 1D TQFT. But once you have non-trivial topological local operators that lead to superselection sector, because each one of them, by the operator state correspondence, give you a distinct vacuum. So in that case, so in 1 plus 1D, all such TQFT actually corresponds to a broken phase. So we don't have, so one way to say it is that option 2 coincides with option 3.
Okay, thank you.
Yeah. In higher D, you have more options. For example, in 2 plus 1D, you can have a Chern-Simon theory. The Chern-Simon theory has a unique local operator, the identity. But then the interesting dynamics are encoded in the line operators, namely the Wilson lines of the Chern-Simon theory. Okay, so that was a very general introduction, and let me now move to examples. So I'll start with quantum mechanics. I'll begin with a general discussion about global symmetries in quantum mechanics, and I'll give 2 examples of quantum mechanics with anomalies. So let's start with what we mean by a global symmetry in quantum mechanics. A global symmetry in quantum mechanics is an anti-unitary or unitary operator that commutes with the Hamiltonian. For simplicity, I'll just talk about unitary global symmetries in bosonic quantum mechanics. In quantum mechanics or in any general quantum systems, we should talk about operators separately from the state. Even though they are related, it's important to discuss them separately. The operators are acted by conjugation by the global symmetry. What I mean is that if I have an operators in quantum mechanics, the global symmetry act on it in this fashion. The global symmetry is defined such that it acts linearly or faithfully on the space of operators by conjugation. By linearly, I meant if I perform this conjugation operation twice, then it's the same as acting the conjugation once, but with a different group element. And there's no phase here. This is a literal equality. This is what I meant by linear representation. On the other hand, UG, this symmetry operator, can act on the state in a projective manner or in a linear manner. Namely, if I act UG2 and UG1 on the state, there can be a phase generally here. Of course, we are always allowed to rescale our operator UG by a phase. And that rescaling will change this phase over here. By this rescaling, sometimes we are able to get rid of this phase completely. In that case, the states are in a linear representation. But there are some other times this phase cannot be removed by such a redefinition of UG. And in that case, this is a true projective representation. So put it differently, this projective phase is characterized again by some cohomology question. It has to satisfy some associativity condition and is subject to ambiguity by rescaling the operator UG. And the non-trivial projective representations are classified by elements in that cohomology group.
This is H1 cohomology, is it?
Is actually H2.
Okay. There's also H1 potentially.
So the reason it's H2 is basically because we have to put in 2 elements here.
Yeah, okay.
And the ambiguity is exact 1 cocycle. And the fact that it's U1 coefficient is because this is a base. So indeed, yeah, I was trying to avoid the more formal mathematical description, but indeed, the anomaly for a unitary global symmetry in a bosonic quantum mechanics is classified by the projective representation of G, and that's mathematically given by H2. So here, let me just repeat what I just said. If UG acts projectively on the state, we say that there is a Tahoef anomaly of the global symmetry. If instead it acts linearly on the state, then we say that there isn't any anomaly. These are just words. But why are this the appropriate definition of an anomaly in quantum mechanics? Let's recall that the Tahoef anomaly is defined as an obstruction to gauging. Gauging in quantum mechanics corresponds to simply projecting to the symmetric sector under the global symmetry. Note that this is generally not true in field theory. In field theory, in higher space-time dimension, gauging is more than just projecting to the symmetric sector, but in quantum mechanics, that's the case. Now suppose the symmetry acts projectively on our Hilbert space. Then there isn't any G invariant state at all. Therefore, we cannot perform this projection. This should therefore be viewed as an obstruction to gauging in quantum mechanics. And that's the reason why a projective representation in quantum mechanics should be interpreted as an anomaly of the global symmetry. So finally, we can talk about examples after all this abstract discussion.
So there's a simple question.
Yeah, go ahead.
If the representation acts projectively on some states, should it act projectively on the full Hilbert space, or could it be that there is some subsector in which it acts faithfully?
I think it's only consistent if it acts in the same projective representation on the whole Hilbert space, because, for example, we can add states together. Right? So if they are in different representation, then there would be a contradiction. But the Hilbert space is a vector space, so we can take a linear combination of state.
Okay, thanks.
Of course, you can talk about twisted sector, but then say in higher dimensions, then it will be different. Hopefully, I will have time to talk about it. Okay. So finally, we can talk about example. And the first example is really trivial. It's just a single qubit. So this is a quantum mechanics. My Hilbert space is 2-dimensional. It has a spin up state and a spin down state. And the Hamiltonian is given by the trivial Hamiltonian. So they have the same energy. The operators in this quantum mechanics are the Pauli operators, sigma x, sigma y, sigma z. The operators are in the 3-dimensional representation of an SO3 global symmetry. And of course, the SO3 global symmetry operators are just exponentiation of the sigmas. However, the states are in a 2-dimensional representation of SU2. In other words, it's in a 2-dimensional projective representation of the SO3 global symmetry. So in that sense, a single qubit has an SO3 global symmetry with a Tahoef anomaly. This is the simplest possible example of an anomaly in any quantum system. Based on this example, let's make some comments about some common prejudice of anomalies. We often hear people saying that anomalies are necessarily tied to the following. First, there have to be fermions. That was the the way that anomalies was first discovered in high energy physics. Second, people usually say anomalies are necessarily tied to the fact that we have infinite degrees of freedom in the continuum theory. While this characterization might be true for some anomalies, it's certainly not true for every anomaly. As we have seen, a free trivial bosonic quantum mechanics, namely a single qubit, can have Tahoef anomalies. Okay. The second example, which is also a quantum mechanics example, is a particle on a ring quantum mechanics. This was nicely discussed in these papers. I'm sure there are earlier references, but I think it was put into this new perspective in these papers. So what is this quantum mechanics? It's a quantum mechanics of a free particle propagating on a circle. The coordinate of this particle on the circle is denoted as x of tau. Tau is the Euclidean time of the quantum mechanics. It's on a circle, so x is identified with x plus 2 pi. The first term is just a standard kinetic term. There's nothing fancy about it. The second term is a theta term with the coefficient theta. It's linear in x dot. This is a total derivative term, but it's non-trivial because x can wind in space. We can have some Euclidean configuration such that when we change tau around the Euclidean time, the target space circle is wrapped many different times. And because x has 2 pi periodicity, theta is identified with theta plus 2 pi. Namely, in the absence of any background field, this quantum mechanics with theta is the same as the quantum mechanics with theta plus 2 pi. In any case, this is a free quantum mechanics. The Lagrangian is quadratic, and we can solve it completely. Let's talk about the global symmetry of this quantum mechanics. Oh, I'm missing an m here. So I might have set m to be 1 in the following. For any value of theta, there is a global symmetry U1 that shifts the field x to x plus alpha, where alpha is on U1 phase. This is a symmetry for any theta. When theta is 0 for pi, there's a more subtle symmetry that flips the sign of x. When theta is 0, we don't have this term, and obviously flipping the sign of x is a symmetry. That's it. We will call this symmetry a charge conjugation symmetry. When theta is pi, this is also a symmetry because theta has 2 pi periodicity. So if we flip the sign of x, we go from pi to minus pi, but then that's identified with minus pi plus 2 pi, which is pi. So let me just repeat. At theta equals to 0 or pi, the global symmetry of this quantum mechanics is a U1 and a charge conjugation. Together, that combines to an O2 global symmetry. The O2 global symmetry acts linearly on the operators. The way they act is given like this. And you can check this by definition, give you the O2 group. However, at theta equals to pi, there is an anomaly of this O2 global symmetry. One way to see the anomaly is, as we outlined in the general introduction, is to couple the quantum mechanics to background gauge field. But here I'm only going to couple to the U1 background gauge field, which I denote by A tau. The way it couples is very simple. We just shift x dot by A tau. So this is the final Lagrange. And you can check that it's invariant under the U1 background gauge transformation with a background gauge parameter lambda of tau. So far, we haven't said anything about the charge conjugation. There isn't a charge conjugation symmetry for general theta, but there is one when theta is 0 or pi. At theta equals to 0, we don't have this term. And this Lagrangian coupled to the background U1 gauge field is invariant under the charge conjugation symmetry, provided you also flip the sign of A tau. So there isn't any anomaly of this O2 global symmetry when theta is 0. At theta equals to pi, however, we see that it's no longer a symmetry because the periodicity of theta is ruined by the presence of A tau. So this is the simplest way to see that there's an anomaly between the charge conjugation symmetry and the U1 global symmetry at theta equals to pi. You can easily check that such a non-invariance cannot be remedied by adding any 0 plus 1D local counter term. The only 0 plus 1D local counter term you can possibly add is this. It's like a one-dimensional Chern-Simons term for the quantum mechanics. But it cannot remedy this non-invariance under the charge conjugation symmetry in the presence of the U1 background gauge field. There's another way to see the anomaly by solving the spectrum of this free quantum mechanics completely and figure out the action of U1 and C on the state. And if you work, and this was worked out in this paper. And if you work this out, you can see that the way the U1 and the C symmetry are realized on the Hilbert space is not O2, but a different group, an extension of O2. And that signals the anomaly when theta is pi. So let me present the answer for that. I think I said M to be 1 here again. So the answer to the homework is that the spectrum is given as follows. It's labeled by integer n, and it depends on theta in this manner. When theta is 0, the energy spectrum looks like this. There's a unique ground state with the lowest energy. When theta is pi, the spectrum is doubly degenerate. And that's actually a consequence of the Tahoef anomaly. Because as we said, when there's a Tahoef anomaly, it means that the low energy phase cannot be trivially gapped. It cannot be a unique ground state with no non-trivial topological quantum field theory. In this particular case, when theta is pi, the anomaly is compatible with the low energy phase in the manner that the charge conjugation symmetry is broken on the ground state. So above, we talk about the anomaly between the U1 and the charge conjugation, but it will be useful to consider the anomalies of a subgroup. And that will be useful when we talk about the dynamical consequences of this anomaly. So let's just talk about the Z2 subgroup of the U1. So instead of shifting X by an arbitrary phase, let's just shift it by a pi. This is a Z2 action, because if you shift it twice, it goes back to itself. So at theta equals to 0 and pi, the quantum mechanics has this Z2 symmetry U and the Z2 charge conjugation symmetry C. They generate the Z2 cross Z2 subgroup of the O2 global symmetry. Again, the Z2 cross Z2 acts linearly on the operators, but when theta is pi, it acts projectively on the Hilbert space. And part of the homework is to realize that when they act on the state, there's an important minus sign here. When acting on the operators, there's no minus sign. U and C simply commute with each other. But when acting on the state, there's an important minus sign. And that minus sign signals the projective representation of Z2 cross Z2 acting on the Hilbert space. And that's the hallmark of the anomaly for this Z2 cross Z2 subgroup. And now we can add interaction to perturb this free quantum mechanics. We can add any potential that's a function of cosine 2x. Obviously, this preserves the Z2 cross Z2 because recall that the Z2 either shift x by pi or flip the sign of x. And cosine 2x is invariant under that Z2 cross Z2. However, we can imagine turning on this potential very slowly with a very small coefficient and then crank it up. But this minus sign cannot disappear all in a sudden. And that's the rigidity of the Tahoef anomaly in general. So we know that, so it follows that for any such potential, the Z2 cross Z2 is still realized projectively on the Hilbert space. And because of this minus sign, we conclude that the spectrum cannot be gapped with a unique ground state for any such potential. This is because this algebra is simply incompatible with a one-dimensional representation. Just to make that clear, if you have a state that if you have a one-dimensional representation of this state, then the eigenvalue of C and U, let's call them A1 and A2, but then this is manifestly incompatible with this algebra. So before this slide, we were just talking about free quantum mechanics, and we derived the spectrum. We can derive the spectrum directly by solving the quantum mechanics, or we can conclude, we can get some clue from the Tahoef anomaly. But now we are saying something more non-trivial about general interacting quantum mechanics, which is generally difficult to solve. But just based on the analysis of this Z2 cross Z2, we can conclude that this scenario is never possible. So this is one of the simplest consequences of Tahoef anomaly on the dynamics of the model. Okay, so let me summarize this part of the discussion. So global symmetry G in quantum mechanics acts linearly on the operators by conjugation. That's how we define the global symmetry. When G acts linearly on the state, we say that there's no anomaly. When G acts projectively on the state, then there's no G invariant state in the Hilbert space. This should be viewed as an obstruction to gauging, and we say that G has an anomaly. And we discussed two examples of anomalies in bosonic quantum mechanics. The first one is a single qubit with trivial Hamiltonian. In that case, the global symmetry is SO3, but it's realized projectively as on the Hilbert space. The second case is the particle on a ring with theta equals 2 pi. This global symmetry is O2, realized linearly on the operators, but it acts projectively on the state. And in the second example, we see that the anomaly leads to non-trivial constraints on the spectrum when we add interactions. All right, so that's the first part about anomalies in quantum mechanics. Is there any other question, or should I move on to the next topic?
I have a couple of questions. So in the second case, you nicely showed that one can see that there's anomaly in two languages, both from the path integral point of view and from the spectrum point of view. So in the first case, it was very easy to see that there was an anomaly from the spectrum point of view. But in that case, just as an exercise, could we also derive it in the path integral point of view? Maybe you would like to leave it as an exercise or something. So is it interesting to do?
I thought about doing that at some point, but yeah, but then so yes, there is a way, but I didn't work it out. So in the first example, I presented a model in the Hamiltonian language rather than the Lagrangian or path.
Yeah.
But it could be represented in the Lagrangian formulation. So can write a simple Lagrangian for it. Where P and Q are two pi periodic. I have to think a little bit about how to couple to the SO3 background gauge fields, but I think it might be easier to do the Z2 cross Z2. I didn't work it out, so let me not improvise here, but there
Okay.
should be a way to do it in this language as well.
Okay.
Can I make,
And yeah,
sorry. I mean, you discussed the distinction between the group multiplication of the operators and what happens when you act on the states.
Right.
Nevertheless, if you have some kind of classical symmetry, which you then implement by unitary operators acting on some Hilbert space, then in a lot of literature, you say the anomaly appears in how you multiply the operators together without particular reference to the states. So the Hilbert space is always in the background. And so this is the H2 anomaly, but there's another anomaly where the operators act on the states in the way it implements on the states gives you the H1 anomaly. I don't know whether this is almost, it must be equivalent to what you're saying, but I think there's a slight distinction.
I'm not sure which H1 are you talking about? Is it?
Well, I mean, supposing you have some wave function and the operator acts on the wave function by acting on the X with the action G, then you can have some phase appearing on the wave function itself, which you can potentially absorb in the operator if H1 is trivial, but not otherwise. I mean, maybe I just adding some confusion here, but I thought you could sort of more abstractly talk about the way in which the operators multiply together and only realize the classical symmetry up to some phase here. I mean, so the equation you got at the bottom of this page, you would write without any particular state psi appearing. This would be a general feature of the operators acting on the Hilbert space.
Right, so this should be true for all states. It should be the same phase for all states.
Yeah, okay, in which case the state psi is not kind of, I think I'm making a distinction between the classical symmetry and the unitary operators, and then you could just drop the state psi there.
Okay, yeah, so yeah, in my presentation, I try to define, I think people might have different notion of global symmetry in quantum mechanics. And that's kind of at the whole discussion, what the whole discussion is about. And here, the way I define the global symmetry is by the group when it acts on the operators. And then the way it acts on the state might be a different group, but we define the global symmetry as the way it acts on operators. So for example, in the Z2 cross Z2 case, in the particle on a ring, the symmetries that acts on the operators in the linear faction is Z2 cross Z2. On the state, it's a projective representation of Z2 cross Z2, which you can think about as D8. Now, some people might prefer to call the global symmetry of this quantum mechanics as D8 rather than Z2 cross Z2. But in a manner that's more compatible with the higher dimensional analogs, it's kind of more natural to call this the symmetry Z2 cross Z2. But these are just words.
Yeah, I agree, just words. But perhaps a more substantial question. The examples you gave were related to the fact that the symmetry group wasn't simply connected. Is this generally the case in quantum mechanics?
I don't think so. Well, here I just gave two examples. But the general statement is that it's given by this H2. I don't think that assumption is necessary. The
for
general
example, would it be true that if G is connected and this H2 is trivial? You gave two examples in which one was G was not simply connected, and in the other case it was discrete. So maybe there is some truth to it.
But I think the existence of the anomaly has, well, at least for this particular anomaly, only concerns H2. I don't see the relation to H1. Maybe there's something else there.
Okay.
Yeah, but if it was a continuous group, then I think if it was simply connected, the anomaly has to be trivial.
That's true.
Or because of some spectral sequence flow.
Yeah.
Yeah, okay.
or continue simply connected groups.
Oh, I see. I see what you are asking. I see. I see. Yeah. Okay. Thank you. Okay. Yeah. Thank you for the question.
I also had another small question. Do you have time, or should I postpone to?
Go ahead. Go ahead. I'm in no rush.
Yeah. So this last example that you gave with this potential, right? So you said if you are slowly cranking it up, then the ground state has to stay doubly degenerate because of the argument that you gave. Yeah, here.
Right. Right.
But then, as we slowly cranking it up, at some point we can it happen that at some point some excited states will also become degenerate, so that the ground state will become now even more degenerate? Such things can happen, right? Your argument does not exclude that.
Yeah. So I think I leave. there's this option here.
Well, in quantum mechanics, it's probably not going to happen, but at least in this example. But for example, two states up, can they merge with the state?
No, in quantum mechanics, this can be the case, right? I can give a very sophisticated example, the BFSS quantum mechanics.
Yeah, but not in this particular case that you gave.
Yeah, not in this particular case, yes.
No, I was just wondering that once you came, in this particular case, once you go through this merger,
right,
and then you go further, what happens further is, are all bets off? Like, could you still have, like, after this merger of the ground states with excited states, could then on the other side of this merger, could there be a unique ground state, or is it still excluded?
And it's still excluded, right? As long as the anomaly and the symmetry is there, then then
I guess so.
Right.
Okay, thanks.
Yeah.
No more questions from me at least.
Okay. Okay, so I have 5-6 minutes left. Maybe I can say a little bit about the next lecture, and we can continue tomorrow for the rest. So now we're moving to 1+1D. And I will only talk about the free boson theory, which might appear to be trivial, but it's extremely rich. So I'll start with some general discussion about the global symmetry and the T-duality of the 1+1D C equals to 1 CFT. And then I'll talk about the Tahoef anomalies, and then some comment about holomorphicity and rationality. So what is a 1+1D free boson? Well, it's what it means is we have a free Lagrangian, the standard kinetic term. I wrote it in Euclidean signature. Phi is dimensionless, is 2π periodic. There's a coefficient r squared here, and that's usually called the radius of the target space S1. So the target space is a circle, and you can absorb this r into the definition of your phi, and then phi lives on a circle with radius r. This r, from the worksheet point of view, is dimensionless, and it's an exactly marginal deformation of the CFT. So different r's labels different CFTs. And this is a CFT with central charge 1. Despite being free, this is actually an extremely rich family of CFT with interesting global symmetry and Tahoef anomalies. And it arises as the low energy effective field theory of many condensed matter system. For example, it could be the low energy, it's the gapless phase of the XY lattice model. So let's go through its global symmetry. There's a U1 global symmetry, which I'll call the momentum symmetry. This is the string theory terminology. What it does is to shift phi by a constant. That's obviously a symmetry. It has a Noether current given by this. The Noether conservation equation is just the equation of motion for the free scalar field. What's less obvious is that there's also a U1 winding global symmetry, where the Noether currents are using the same set of operators as for the momentum, but you exchange the role of time and space. And you also normalize them differently. The normalization will become important later. The conservation equation for the winding symmetry is trivial because if you hit another derivative and use the anti-symmetry property of the epsilon tensor, it just trivially vanishes. It's like a Bianchi identity. Finally, there's an interesting Z2 symmetry that flips the sign of phi, but I will not talk about it in this talk. In other words, I will not go to the orbifold branch. I will stay on the c equals to 1 as the circle branch. All right. So the momentum symmetry is quite manifest in this presentation. It shifts phi by a constant. The winding symmetry is more mysterious. So let's try to understand it better. Let the space of our 1 + 1D free boson be a circle of circumference L. A classical winding configuration is given as follows. So it's linear in the coordinate x. So as you increase x from 0 to L, it doesn't go back to itself, but phi goes to phi plus 2 pi w. This will be an acceptable configuration if w is an integer. This is because phi, as defined here, is circle value rather than real value. So this is an allowed winding configuration with integer w. Quantum mechanically, this classical configuration corresponds to a winding state carrying a non-zero winding charge. What is the winding charge? You take the nether current, the time component of it, you integrate it in space. The time component is given by this, and that just measures the number of times this winding configuration wraps around in space. But still, it's kind of mysterious. Well, what does the winding symmetry act on anyways? I have identified a configuration for you, but I didn't tell you what kind of field this winding symmetry acts. Well, it actually does not act on phi or any of its derivative or polynomials. Rather, it acts on the dual field. So to talk about that, we have to say a little bit about the T-duality. So what do? So we first rewrite a free boson Lagrangian in this manner. So what we introduce is a field V mu and V tilde. V tilde mu is a Lagrange multiplier. When you integrate it out, it sets V nu to be the derivative of phi. And then you plug this back in, you retrieve the original free boson Lagrangian. But instead of integrating out V tilde nu, which was introduced as a Lagrange multiplier, the trick of duality is that you integrate out something else. So here we integrate out V mu instead. And then you find the following equation. And you insert this back in, you can rewrite this Lagrangian in the following form. So note that here, in going from here to here, we kind of exchange V with V tilde. Importantly, R squared originally was in the numerator, now it's in the denominator. And here I purposely write phi this way so that it looks like a Lagrange multiplier. So we're switching the roles of all these fields. Originally, V tilde was a Lagrange multiplier. V mu is just another name for the derivative of phi. But now we integrate out V mu, and phi now looks like a Lagrange multiplier. It used to be the fundamental field. Since it looks like a Lagrange multiplier, we are going to integrate it out. Integrating phi out, we get a constraint that this vanishes. And that can be locally solved in terms of a dual scalar field phi tilde. Here I put a sign just for convenience. It doesn't mean anything significant. So now we have run into a dual field. Let's plug this back in. And we get another free compact boson Lagrangian. But now the R square is in the new denominator. And you can actually check that phi tilde. Oops, missed a sign here. You can actually check the phi tilde is 2π periodic by matching the global winding charges. So what do we what have we found? So this slide is a little bit computational intensive. So I went through it rather quickly, but it's actually quite fun to go through it slowly. But at the end of the day, what we show is that this free Lagrangian with R squared in the numerator is actually equivalent to the free boson Lagrangian using a different field with R squared in the denominator. And that's the famous T-duality in string theory, where the radius R is the same as 1 over R. So the CFT, the free boson CFT is labeled by this exactly marginal deformation, but the one labeled by R is actually the same CFT as the one labeled by 1 over R. So the moduli space looks as follows. We have a R axis. Naively, you might think the moduli space is the conformal manifold. Naively, you would think this branch of the moduli space is just the real value, R, or maybe not real value, but let me see how to say this, at least a positive value. Well, actually, let me erase that. In any case, naively, you would think that it goes from 0 to infinity. But what you have learned is that these 2 points are identified. So the moduli space actually looks like this, where this is 1. Okay. Let me see if I want to. Oh, let me finish the lecture today with this final slide. Okay, so the homework is you can go through this derivation on this slide. Here I relate V with phi, V tilde with phi tilde, blah, blah, blah. But V and V tilde are kind of just, they are not the main players. They're just there they only appear in the intermediate steps. The real interesting question is, what's the relation between phi and phi tilde? The answer is given here, but it's actually kind of fun to work it out by following the above steps. And because of this relation, we see that the T-duality exchanges the momentum and the winding symmetry. Since we know U1 momentum symmetry shifts phi, it follows that U1 winding symmetry shifts the dual field phi tilde. And that hopefully demystify this winding symmetry a little bit. Okay, I should stop here and I'll continue 1 + 1D free boson tomorrow. Thank you.
Thanks very much. Well, we have time for questions, certainly. So,
is it too slow or too fast at the right pace?
I personally enjoyed it. So,
thank you.
Yeah. I think we have people.
Zohar,
most of the people stayed until the very end. Well, Zohar is not a typical audience here.
Oh, he was saying something, but his lips were moving, so I was asking.
It was not a hand raise, it was clapping.
Oh, okay. Oh, sorry. Oh, sorry. Okay.
But people should not hesitate to ask questions. If not, then people can also ask them on Slack. So
yeah, I'll check Slacks regularly.
I do have a kind of general question about this T-duality. So
Yeah.
can we generally expect that if we have some, let's say, even free theory, and we have different global symmetries that have the same group, like here we have two U1s, can we expect that there will be some T-duality exchanging them in general? Like, for example, if we add, if we instead had two SU2s, or if we have even more, like 3 U1 symmetries, and we must be able to permute them.
I don't think that's generally the case. Yeah.
Okay.
Right. I mean, for example, maybe it's easy to give some trivial example, right? So you take a CFT with a Z2 symmetry, you take a different CFT with a Z2 symmetry, tensor product the two, but there's obviously no duality a priori exchanging the two CFT. I don't think it's generally the case. Sometimes it might be the case.
Thanks.
Perhaps it's worth saying that there is a generalization of this to toroidal sigma models of arbitrary target space dimension.
Certainly, yeah. So here I'm just working with C equals to 1, and more generally, you can take a bunch of free bosons, and then the target space is a n-dimensional torus. And then you can start turning on different exactly marginal deformation. You can make one of the direction in the target space longer, make the other one shorter, or you can start to bend them. And even more subtly, there are some what is known as the B field margin, exactly marginal deformation.
Yeah, and then one will go into having an array in CFT.
That's right.
Yeah, with the modular space.
Yeah. And here I just started with the simplest possible one. Already here, there is an interesting anomaly, as we will discuss tomorrow.
Good, thanks.
Yeah, thank you.
Shu-Heng, I have a question about the T-duality in the last page.
Yeah.
Well, maybe one more.
One more.
Yeah. So when you integrate out the V mu, which is derivative of phi, so intuitively, what the remaining degrees of freedom for phi is should be some constant field, but in the last step you still do some variation with respect to phi. So can you explain more on this?
Well, I think that's not completely precise. So because all these relations are on-shell relations, but when we integrate our fields, we are working with everything off-shell. So it's not quite precise to say that if we integrate our V mu, we restrict phi. Right? This relation is only true if you first integrate our V tilde mu. Originally, V tilde mu was introduced as a Lagrange multiplier, and therefore it was tempting to integrate it out and enforce this operator equation.
I see.
But here we decide to take a different route by keeping V tilde mu, but integrate our V mu. And since we keep V tilde mu, this on-shell equation is not dictated upon us.
I see. Thanks.
Can I ask a basic question about Abj anomaly? So, so the fact that it's not a true symmetry, can we see it from this point of view of coupling to background gauge fields, as we saw for?
I think that's an interesting question. So, well, the answer is yes, but I think there's an interesting way to answer that. Well, so here for Abj anomaly, the statement is, of course, that if you take this operator for the axial current, so this is the axial U1 global symmetry, and let me put symmetry in quotation mark current, because it ends up not being a symmetry, you'll find that this equals to some number, f wedge f.
Yeah, yesterday somehow it's extremely hot after the end of the talk.
Oh, sorry, was that a question or? Oh, okay. Should I continue or Everything good?
I think somebody just spoke by mistake with his mic unmuted. You should go ahead.
Okay. Right. So this is the famous anomalous conservation equation, right, for the ABJ. Except that, or maybe I should be consistent. It's a little lowercase. Except that here F is not a background gauge field, it's a dynamical gauge field. So there's no sense that you can turn it off. For global symmetry, then the right-hand side will be for Tahoef anomaly, namely the first case. Then on the right-hand side, you have capital F, wedge capital F. And this is a background field and you can turn it off. And when you turn it off, you have an exact Noether conservation equation. But for ABJ, this is the operator. It's a non-trivial operator in your theory. And there's no sense you can turn it off. And therefore, the axial symmetry is not really a symmetry. It never obeys a conservation equation.
Thank you.
And the related point is that I think ABJ anomaly is difficult to phrase it completely abstractly. It kind of relies on a weakly coupled frame or description of the model. We were misguided to think that there is an axial U1 global symmetry because there's a weakly coupled description of the QED. And from the weakly coupled Lagrangian, it appears as if there's an axial U1 global symmetry. But completely generally, since the symmetry is not there anyways, it's not clear what to talk about anyways. By contrast, Tahoef anomaly is completely abstract and general. No matter which presentation you use for the model, there will be a global symmetry current. And you can meaningfully talk about its Tahoef anomaly.
But Shu-Heng, if I understood Antonio's question correctly, perhaps he just wanted to hear you say that in this particular case, we have actually a Tahoef anomaly between U1 axial and U1 vectorial. And since we have that Tahoef anomaly, when we gauge U1 vectorial, we end up with Abj anomaly.
That's right.
So in fact, there is a relation. There's a logical.
That's right. So so let me just write it. So we can take the example here to be QED. Here a massless QED. And here to be a massless Dirac fermion. That's right. But but I think it's important to distinguish these two models, right? So a free Dirac fermion is different from QED. They're related by gauging. This model doesn't have an axial global symmetry. Yeah. But this other model, this free Dirac fermion, has a Tahoef anomaly by choosing this to be axial, this two to be vector. So indeed, this Abj anomaly can be understood as the Tahoef anomaly in a different model. In that different model, it can be understood in terms of the anomalous background gauge transformation. Yeah, so that's absolutely yes.
If you change the axial current by something which is not gauge invariant, you can cancel the anomaly, can't you? Because you can write F wedge F as D of something.
Yes. It's a good point. Yeah, let me think about how to say it. But I thought there's.
Hope not.
I think this is related to the idea that you can move the anomaly around between different currents.
Right, but then I think then the problem is that that's not a good local operator, right? So what you are suggesting is that we can.
F wedge F is D of something local. I mean, I think the point here is that you have to maintain the vector current as non-anomalous in order to gauge it if it's dynamical.
I would say slightly differently. Sigma coefficient A, oops, not A nu 0 sigma. Right, that's the thing you have in mind. Right, this guy would then be conserved. Right?
Sure, that would be conserved if you choose it appropriately.
But the problem is that this is not a gauge invariant local operator. This guy's not. This one is, but this is not.
Yeah, but you have some sort of idea that you need to make these operators gauge invariant, which is perhaps true if you want to couple it to a dynamical gauge field.
I wouldn't say it that way. I think generally when I think about any quantum field theory, I think about the spectrum of local operators. And by definition, local operators should be gauge invariant. And I simply refuse at this level of the discussion to talk about gauge non-invariant operators. In a particular weakly coupled frame Lagrangian, we can say that, oh, there's this field that's not gauge invariant. But completely abstractly, I work with gauge invariant local operators. And then this guy doesn't qualify. So I would still say that there's no axial global U1 symmetry in this model. The invariant statement is that in the QED, there isn't any gauge invariant local Noether current.
But couldn't we just, yeah.
Probably, I mean, I think Hugh is just thinking about the theory in which the U1 is not gauged. So it's probably, you seem to be.
Okay, then we are talking about a different model. Yeah, so certainly. So that's why I think I made it very clear in the beginning that we should really distinguish the model with T and the model with T prime. They're related by gauging, but they're really two distinct models.
Is it correct, Hugh? I think it was.
Yeah, I think that's more. I mean, I think it was a quibble rather than maybe a big point. But I mean, there are these. I mean, the point is, in this theory, you have two currents, namely the vector current.
Well, in which theory? I think that's the question.
But in the theory, which is coupled to a gauge field, right? The gauge field is coupled
to a dynamical or a classical gauge.
Well, it's coupled to a vector current. And
so which theory do you have in mind?
Well, I'm thinking of fermions coupled to a vector gauge field.
Is it a dynamical vector gauge field or a classical vector gauge field?
A dynamical.
Dynamical, you said?
Yeah, yeah. In which case you have to have a vector current, which is gauge. When you regularize the theory, you have to do it in such a way to define the currents.
So then we are talking about this column, right?
Yeah, yeah.
So you have a fermion. You have a fermion coupled to a vector gauge field. But then I maintain the statement that in this theory, there isn't any gauge invariant local Noether current.
I think the issue that he is raising is best described in the leftmost column. I think I would just say
right.
we have a Dirac fermion that has U1 cross U1.
Yeah.
We can fix it up. We can fix it up a little bit, but provided that we insist that fixing up the Dirac that U1 vectorial doesn't have a Tahoef anomaly, we will always find that U1 axial will have a Tahoef anomaly with U1 vectorial.
In the leftmost theory, it's a free Dirac fermion, massless, and it just has two U1 global symmetry. One vector, one axial. We have an independent local conserved Noether current for each one of them.
I can try to rephrase it, I think, in a more maybe simple way.
Sure.
So if you look at the free fermion, you can compute various 3-point functions for global symmetry currents. Axial, vector, vector, all the combinations.
Yeah.
The statement is that there is a scheme by adding local counter terms in terms of background gauge fields, where the conservation equation for the vector current is obeyed, including at coincident points.
Yeah.
But the axial symmetry is not in that scheme. It's not possible to obey the axial symmetry at coincident points.
Yeah.
Yeah, certainly.
That's what it means to shift the Chern-Simon space to the left-hand side. It doesn't make sense after you've gauged the vector symmetry, but it makes sense to do it for background gauge fields because it corresponds to a change of scheme.
That's right. That's certainly right. But that will be on this column.
For sure, for sure. Just that on this column, yeah, there are ambiguities in which variations are anomalous and which are not. If there are multiple symmetries and multiple variations, you can add common trivial terms to shift things around.
That's right.
Yeah. Yeah. Okay, I see Balt wants to ask something.
Maybe a more philosophical question. So in your first example, you say like your SO3 was anomalous, but it was, you can lift it to an SU2, and the SU2 is not anomalous.
Right.
And your second example had a similar thing, and I think this is a more general thing, right? The projective representation, you can just lift it to a representation of the central extension.
Yeah.
So
I'm a bit confused about this. How is SU2 non-anomalous? Because for SU2, there is no invariant ground state either.
that's correct, but it is not projectively realized. It acts as a proper non-projective representation. So indeed, the statement is this SU2 acts on the Hilbert space, and there's no singlet in the Hilbert space.
But then I don't. Then it becomes useless. So Shu-Heng said that physically, if some symmetry is anomalous, then there is. It means that if some symmetry is not anomalous, then it means that there is an invariant vacuum, and vice versa. And here you say that this classification, this beautiful explanation, goes away.
I thought Paul was not using the term anomalous versus non-anomalous. I thought he was just saying that we can. There's a SO3 acting linearly on the operators, and there's a SU2 also acting linearly on the state. And then we can decide what we mean by anomalous or non-anomalous. But maybe let's put that word aside for the time being.
Right. SU2 symmetry doesn't act on. I mean, it's like taking a QFT on which U1 doesn't act and saying that it's a symmetry. SU2 is just not a symmetry. SO3 is the symmetry.
Yeah, in this definition, yes. But yeah,
but the U1 does not, in your example, does not act on the Hilbert space. The SU2 that I have in mind acts on the Hilbert space.
No, your SU2 is not acting faithfully on the space of local operators. Even in the Bootstrap, we want the symmetries to act on some local operators. If there is no local operator which is acted upon by the symmetry, then you don't call it a symmetry.
That is one way, sure. I guess my question is, I can have this alternative viewpoint where I say I just see what acts on the Hilbert space, which would be a central extension of what you would call a symmetry.
So, but one crucial point is that if you view this view the symmetry as SU2, then the center of that SU2 is always acts as -1 on the Hilbert space.
Yes, that's correct.
And I mean, I agree. As I said, I think these are just words. And here I'm giving a very streamlined definition of what my words mean. Yeah. So I define what symmetry means and what anomalies mean. And people might have different notions of symmetries and anomaly. But this particular definition actually works pretty well with the higher dimensional generalization.
That's why my question was a bit philosophical. I guess my viewpoint would be there's a gigantic, well, my somewhat controversial viewpoint, which I would not teach my students, but there could be a viewpoint where you say there's a bigger symmetry group that acts on the Hilbert space under which there's no state invariant.
But can I make a philosophical remark too on this?
Please.
Actually, you might think that SU2 is a bigger symmetry, and you're of course correct. But the space of gauge fields to which you can couple SU2 is smaller than the SO3. It sounds counterintuitive, but it's true. Do you see why? So to get more information about quantum field theory, you try to couple it to as many sources as possible. By saying that the symmetry is SU2, you limit the space of sources to which you can couple the system. And then you cannot learn as much, and it's not surprising. We can learn the maximal amount of things about QFT by coupling it to the maximal amount of sources. SU2 has less sources than SO3 because SU2 has integral fluxes on closed two manifolds, and SO3 allows also for half integral fluxes.
Yep.
So actually, by enlarging the symmetry, you limit what you can do with QFT.
But guys, this discussion has been very confusing for me. So I learned this interesting piece of information that in quantum mechanics, if a symmetry is anomalous, then there's not going to be a unique ground state. That's a nice fact. I'd like to use this fact, but now if it seems to me that either I keep this fact, but then I better use Shu-Heng's definition of symmetry. If I use Bald's definition of symmetry, it becomes useless. Yeah, so I have
correct. Yeah,
it's a useless definition of symmetry, so we better keep the one which is useful, otherwise the one which doesn't give any interesting conclusions. So I would like to understand why Shu-Heng's definition of symmetry is the correct one. So Zohar seems to be saying that one way to see what is the correct one is that we should have the symmetry to act faithfully on local operators, and this would not be true for SU2.
That's right.
If the symmetry acts faithfully, it allows you to couple it to the maximal amount of sources, and then you can learn many good lessons.
Yeah, okay, but we are talking about definitions, right? So it's I'm happy with the definition that symmetry is something which acts faithfully. I heard it in other contexts. So this
faithfully on local operators.
On local operators.
Right, because we use local operators to couple to background gauge fields.
Yeah. Okay.
Like J-mu, A-mu.
Not faithfully on the Hilbert space of the theory, because that's, according to this definition, is not necessarily.
Yeah, but that's everyone knows in quantum mechanics. The symmetry is not supposed to act, may act projective. That we all learn. So there's nothing.
That's right, and that's why I give a reference to Wigner here.
Yeah. So yeah, so Shu-Heng, you are trying to be diplomatic here, but I think if I were you, I would come out more strongly with saying that your definition is a better one, because
Well, but that's why I presented it.
Okay.
No, but it is one of nomenclature. I mean, there is some representation of a central extension, and this is just what you can find in the math literature. That's what the projective representation, in a sense, is. So these are completely equivalent. So
this is the beginning of very deep questions, because you can go to higher dimensions and try to do what Bald said. Take some Tahoef anomaly in higher dimensions, and you can ask, can I always get rid of it by pretending that I didn't discover all the symmetries, and by adding some generators that are not faithfully acting, right?
Oh, that's what you mean. Okay. Yeah.
That's a very good question. It's actually a very deep question, and there are lots of papers about it.
That's right.
But suppose that I could do it, why would this be interesting?
It's actually related to the question you ask. It's actually related to this point. After engaging, it's not completely obvious based on the discussion, but it's actually related to this point.
It's a very good and deep question that you should ask. In one dimension, it's trivial. Just Bald gave the construction. You just take the central extension of the group.
Yeah.
But in higher dimensions, I believe it's still open. In fact, I discussed it with Shu-Heng a few months ago now.
Yeah, for some cases it's settled, right? But then the most general case is not settled.
Okay, maybe we should then thank Shu-Heng again.
Okay, thank you.
Thanks a lot.
Yeah, thanks a lot for the interesting questions.